Hello everyone, my name is Pablo Samuel Castro. I'm a researcher with Google in the Brain team, and today I'm going to talk to you about my paper GANterpretations. So the idea here is to take a machine learning model that's able to generate something like images and use it to complement some other artistic performance such as music or spoken word or something like that, specifically some audio file. So the way it works is first we start off with the generative model. So I'm using BigGAN for this. So BigGAN is a model that was published a couple of years ago, and it's what's called a class conditional GAN in the sense that we can specify one out of 1,000 possible categories, and the model will generate a sample from one of these categories. So if a GAN is trained properly, it ends up with this latent space that is structured in a way that points nearby to each other will generate similar images. And so what's nice about this latent space that the model has learned is that we can draw paths from one point to another, and this will basically create a morphing from one image to the next. And so I use this idea to create a video to complement an audio file. So what do I mean by an audio file? It could be a sound recording, it could be the audio from a video. For instance, the audio of this video is what I use to generate the GANterpretation that you see to my right here. So the way it works is that first we take the audio file and we compute what's called the spectrogram. So the spectrogram is what you see here. On the rows, we have the frequencies of sound. So these are the different frequencies that you hear, and the combination of these frequencies is what produces the sound that your ears process. And on the x-axis, we have the timeline. So this is as the sound progresses throughout time. So we end up with this two-dimensional matrix where the rows are the frequencies and the columns are the times. And so what I do is I compute the total variation distance from one time slice to the next. So the total variation distance is this well-known measure that gives you a distance between two probability distributions. In this case, they're not quite probability distributions, but we're treating it kind of like they are. So we're really comparing the frequencies in one time slice against the frequencies in the next. And when we do that, we're going to end up with this one-dimensional signal like I have here. So the reason I use this is because now we can look at, you can see there's some peaks and valleys that we have here. So I'm going to pick these peaks and valleys using an algorithm that you can see the details of in the paper. And these peaks and valleys, I'm going to call them inflection points. So for each inflection point, I'm going to pick a category out of the 1,000 possible categories from BigGAN. And so what I'm going to end up trying to do is to draw a path between categories. So if we have, for instance, 55 different inflection points, we're going to draw a path that visits 55 different categories of the BigGAN. Now, how to draw the path between these categories? Well, that's where we use this one-dimensional total variation distance. So we have the inflection points, and now what we can do is we can normalize between the any two inflection points. We normalize relative to the cumulative sum of this one-dimensional value. So what we end up with is a value that goes from 0 at the first inflection point all the way to 1 in the second inflection point. And we do this for all inflection points, and we end up with something as you see below. So now we have this path that goes between inflection points. And this path, what's nice about it is that it corresponds well to the audio that you're listening to. In particular, if I have silences, then that results in little movement. But when I'm talking a lot, the sound is changing from time frame to time frame, which typically results in more movement. So now that we have this path throughout the latent space, what we have to do is pick the categories. So we can do this in a number of ways. We can try to manually pick the categories to match the narrative of what we're seeing, or we can just have the algorithm pick the categories for us randomly, which is what I did for this video. But you can see examples in my blog post of manually curating the set of categories to match a particular narrative. So you can check out my blog post for more examples. I won't have time to show you some more here, but throughout this whole video you will have seen an example. But I'm really excited about how people use this idea. I think complementing one artistic performance with another using machine learning models is quite powerful, and I think there's a lot of other interesting avenues that you can explore starting from this idea. Thank you very much for your time, and I hope to talk to you soon. Bye.